So let's start by covering what the structure of an atom is. So historically, you'll need to understand that basically, we started with the idea that atom was the smallest indivisible unit that made up matter. And you kind of might know that from your chemistry, all right? And, that's basically your Dalton's atomic theory, and, that was preceded by the Greeks, but we obviously know that's wrong nowadays. We know that it can be divided, but that was kind of the theory. And that more or less was our understanding until fairly recently. And by fairly recently, I mean about 120 years ago. And historically, that basically meant that I'll give you a brief overview, then we'll go into a bit of detail. So it basically had the advent of cathode rays, which we then showed were electrons, which were common to all atoms. All right. So due to the discovery of cathode rays in the late 19th century, we then did a fair bit of research, which found that, well, actually, these were things that, firstly, they're particles, and secondly, every single atom has them. So if atoms are the smallest things that make up everything, how can something be like in all the atoms? And so that really challenged the idea that atoms were the smallest possible object or particle. And so that led to the revised Thomson-Plum pudding model. Now, the Thomson-Plum pudding model was then, well, challenged because of the fact that, well, if Thomson-Plum pudding model was correct, then basically we had another experiment where we basically said that you had the Geiger-Marsden experiment. And we'll go through these in a little bit of detail. But basically, due to the Geiger-Marsden experiment, you then got upgraded to the Rutherford model. Now, the Rutherford model had some problems. Again, we'll get into that in a moment. And that's got upgraded as opposed to the Bohr model. And the Bohr model, again, had some problems, which I suppose were kind of revised by, applied to Broglie. So de Broglie didn't really come up with a new model, but, upgraded by de Broglie. And then after a while, we go to Schrodinger's model. So you do need to know each and every model for your atom, right? And how they all relate. And so let's start with cathode rays. So cathode rays, what are they? Well, nowadays we understand them to be just, electrons. All right? So they're negatively charged particles that, are fairly light. Okay. And when they were basically doing, these experiments with cathode rays, they basically had these sort of tubes. They had, an anode and a cathode, and basically applied a strong electric field to it. And basically, they'd find that this part would sort of glow green. And they were basically trying to figure out what made this glow green. And through various experiments, we found that they had certain properties, and it looks like they would travel in straight lines. Despite a bit of a hiccup, we later found that they were deflected by electric fields towards the positive end. They are deflected by magnetic fields. And, they have momentum. and then could cast shadows. And so for these reasons, they later determined, as we said, that it's a negatively charged particle. Some of these experiments, they came up with different results to start with due to the technology at the time. There basically were errors in the experiment. But basically, what we've found now is that these cathode rays are indeed negatively charged particles. And the key thing that made them very, as far as your atomic model theory is involved, the key thing that sort of made it very, very, very difficult for them to say that, there's just an atom and it can't be broken up, is the fact that they changed the cathode. So the cathode can be different material. But as we change the cathode, the cathode rays, as they called them back then, stayed the same. Now they understood that this cathode ray basically meant that there were these things coming from the cathode to create this sort of green glow. And nowadays we would explain it as the electrons coming in and interacting with this sort of glass molecules. All right, that's how we would sort of explain it now. But basically, this material can be changed. It's not set, right? And so we change to different types of metals. And despite changing into different types of metals, we find that the cathode rays stay the same. And for that reason, it is then found, then we say, okay, it must be common to all atoms. And if all atom types are meant to be different, then we basically then say, well, we have found a particle that must be, making up an atom. Right? Because, if this was gold, it should just be made up of gold atoms. If it was copper, it should just be made up of copper atoms, and so on. So you shouldn't be able to get the same thing out of copper as out of gold, for example. So now that we recognize that, hey, we've got something that's sort of new and common to everything, we want to find out a bit more about it. So the scientist that did the experiment is Thomson. And what he found was the mass to charge ratio of, well, the electron, otherwise known as cathode rays at the time. So how did he do this? Well, if you know your magnetic and electric field theory well from what we basically did, was it yesterday or the day before? No, probably the day before at this point, or even Tuesday. Then it's pretty easy. What Thomson basically did was, let me draw it from left to right, all right? So we understand that these cathode rays are negative. So I just draw it as a negative, all right? So you've got your electron, all right? And you've got this sort of box that these electrons will kind of be going through. And basically, we want the electron to we want to be able to measure the charge to mass ratio of the electron. Now, very similarly to what we talked about with, mass spectroscopy in chemistry, basically we apply an electric field. So firstly, There's something else that's moving the the electron from left to right. I'm leaving out that detail, but look, basically, there is the generation of electron, not shown, to keep the diagram simpler. So you've got something that generates the electron and shoots them with some velocity to the right, okay? What we're going to do is, number one, subject the electrons that are moving to both an electric field and a magnetic field. So we skipped over the equations for chemistry, but we will need them for physics. So you understand that the electric field gives Fe, which is QE, and this, in my case, would be upward, in my example here. Nothing hard, just direct application of your, formulas. Now this E is also V over D, but let's leave out that detail for now. Now from your magnetic field, you'll also get another force. So your electric field gives you this force, your magnetic field gives you this force. Now, there's a sine theta, of course, but I'm going to make it simpler. So we're just going to make it so that, well, it's 90 degrees. So there's no sine theta that I need to worry about. So in this case, because I've chosen into the page, and because, the magnetic field is going into the page, because the electron is going to the right, which means positive charge is going to the left, using a right hand, push rule, that really means that this will be going downward. All right. So this is just application of the things we've talked about before. Now, because we both are happening, not just one, but both, then what we then end up getting is one force is pushing up and one force is pushing down. And so I guess the question is, which way does the electron go, right? Does it go up or does it go down? Now, obviously, the answer depends. Because, if this is larger, then it's going to go up. And if this is larger, then it's going to go down. But we're not really interested in going up or down. It doesn't really help us. So what we do is then we adjust the E and the B until the electron passes undeflected. So, this E, if you think about your experiment, this E, you made the E. This E is V over D. You could change the distance between the plates if you, designed it so you could, or you could change the voltage by adding a resistor and all that kind of thing. Like you can vary that. That's up to you. And this B is, created by a current. So again, you can vary that as well. So you can basically tweak both the electric and or the magnetic field until the electron passes through undeflected. That's what you want. And so that's what we do. So that means the condition is Fe equals Fb, which means your QE equals QVB, which means your velocity must equal E over B. And that's basically how your mass spec chooses your velocity as well, right? You apply both the fields together and you end up being able to let only this velocity through to go in a straight line. Because any other velocity would either, go up or go down, because of the fact that the electric field doesn't depend on velocity, but the magnetic field force does. So that's the first step Thomson did. All right, apply both electric and magnetic fields, adjust them until it goes straight, and that's that. So step one, make the electron go straight. After step one, step two, turn off the electric field. Leave only the magnetic field. Now, from what we talked about previously as well, if you have a particle that is charged, and an electron most certainly is charged, in a magnetic field, because we have a magnetic field only, then it will undergo circular motion. And we've also, I mean, I'll quickly show you here, I just quoted you the formula in chemistry, but that means the electron will undergo circular motion. So that means Fc must equal Fb, which means your mv squared over r must equal qvb. And as a result, your r equals your mv over qb, as we mentioned. So that's how we get that formula. But the question is, how does that really help us? Well, this velocity, remember, is set now. This velocity is e over b. Which then means that the radius must equal m. The radius, let me do it this way. So the radius must equal m over q times, we're going to replace v by e over b. So it's going to be e over b squared, right? So that's what we have now. But you have to remember that E is something we know, or most certainly can calculate, because we control the V and the D. So we can calculate E. We can calculate the B, because again, we control that. And we can measure the R, which means the only thing that's not known is the M over Q. So as a result of that, by doing this experiment, so Thomson is then able to determine the mass to charge ratio of cathode rays. And that's basically Thomson's main contribution there. And he also came up with the Thomson-Plum pudding model. Because once you say that an atom is not the smallest single unit, he has to come up with some sort of explanation. So, you know, his idea is basically, well, the atoms, just think of it like a sphere, right? And let's think of it like, it's a cake, right? And inside this cake, there are little raisins, if you like. So, back then, 120 years ago, plum pudding is what everyone sort of, if you're English and so on. But basically, he's just saying, think of it like a cake, right? Inside a cake, you might have little things like raisins, which are just like little bits and pieces that are spread throughout. But overall, they're just stuck inside a cake. So overall, this atom is positive. Like just the general idea of behind an atom is, positive. But you've got these little nuggets, little pieces that are just negative charges that you can sort of knock out. And that was his idea of a plum pudding model. And so, this is the idea. So it is a plum pudding, which is generally positive, with the plums representing the electrons. So he didn't have a whole lot of information to go by. All he knew was that, okay, your atom's not the smallest unit anymore. We've got to put in the electron somewhere. And he just came up with this idea. Now, not too long after that was disproven, and we'll get to that. But before we do, we'll need to talk about sort of another scientist called Millikan. So Millikan also did an experiment which allowed us to, he determined the fundamental charge. And therefore, essentially determined the charge of an electron, and at the same time, also basically figured out as a result what you know, and therefore can use this information to find the mass of an electron, you know, using Thomson's mass to charge ratio. Because Thomson's giving you a fraction, right? Thomson's giving you a ratio between mass and charge. So if you know one of them, which is what Millikan did, then you know the other, all right? So Millikan's experiment is something that we'll need to quickly go through. So basically, it might be a bit difficult to draw, but the idea is quite simple. Basically, what Millikan did is he just, you know, pumped in oil. So he's got an atomizer, and we just, you know, pump in tiny droplets of oil here. So we've got oil. So this is an atomizer. Now, oil droplets will not necessarily all be the same size, all right? So basically, that's a drop. Now, once an oil droplet generally is not charged. Now, we do want it to be charged for reasons that, you know, will kind of become apparent very soon. So basically, we hit these with X-rays. And the aim of that is to make it so that some of them will become charged. And then, once they get charged, they may also when you've got lots of drops, some of them will get through, and hopefully they've charged. And then, once they get through here, what we basically do is we apply an electric field. So we can apply a positive side to this side and a negative side to this side. And basically, the oil droplets become negatively charged. So we've got this oil droplet, it's falling towards, you know, the Earth based on gravity. And then you've got an oil droplet, I'm going to make it larger here. You've got an oil droplet that's kind of falling down, right? Well, it was anyway. But it's got a negative charge thanks to the X-ray from above. And now that is a charged thing, this oil droplet will experience two forces. One is the weight equaling mg, and one is the electric field force, which is QE. Okay. Now, we kind of know G, okay? And basically what we do, what Millikan did, is we basically adjust E until Fe equals W. In other words, until acceleration equals 0. So basically, you know, until the droplet sort of hangs in midair or free fall, either way, but usually midair. It just hovers in midair, the acceleration is 0, it gives you a bit longer to measure it. But basically, the condition is we make it so that the force from the electric field balances out with the weight. Now, then that lets us basically work out Q, because if Fe equals mg, then your Q must equal mg over E, as long as you can work each of those things out. Well, E is probably quite basic to work out. We've covered that earlier. If you know the voltage and you know the distance, you know E. G, we've pretty much worked out. So now the question is, how do you work out M? Well, not too bad. M, we don't need to get into the formulas, but basically they can look at how big the drop is. So they can basically look at the drop size, based on the radius, calculate the volume, and then multiply by density. So without getting too much into the maths, the point is Millikan was able to use this setup and use this method. So basically put in atomized oil droplets, charge them using X-rays, let them enter an electric field. As it drops, adjust the electric field to, measure until it's not free fall, and then, take measurements. And basically the result of all of this is he was able to determine, find out various charges. He, obviously does this lots of times. And he gets lots of values of Q. Okay. All right. So once that once you've basically done that, and you get lots of values of Q, then essentially what happens then is that he finds the charges are all multiple of a basic number. They have a highest common factor, basically. And this highest common factor is 1.602 times 10 to the negative 19. So as a result of this, we then say, well, if all the numbers are multiples of this, then this is your fundamental charge. And we're basically saying, okay, so every time you gain or lose a charge, at least at that point in time, at the electron level, it's going to be this, which means that is the charge of an electron. Okay. And that's basically how he worked out the charge of an electron. Combined with Thomson's, mass to charge ratio, we were also able to find the mass of an electron. So that's basically Millikan's experiment. So after Millikan's experiment, we basically should go back and talk about essentially your model of the atom. I assume there's no questions, so I'll just keep going. If there are, you should type them out so I am aware. So after Thomson's plum pudding model, there was this experiment done. Okay. And this is called the Geiger-Marsden experiment. Okay. And basically, what did this experiment do? Well, basically what this experiment did was it fired alpha particles at a gold foil. And then basically looked at what happened to that. So basically they had detectors that went around. So you had a detector that was, mobile. And so you could basically detect, and it kind of went all the way around. And so basically it would just detect where did the alpha particles go, all right? So essentially we, fired alpha particles, which remember are helium atoms, which are considered relatively heavy, or nuclei, I should say, at gold foil. And therefore, after finding the alpha particles at gold foil, we basically detected the angles of deflection and their probabilities. Now, the results were quite surprising for them, because what they basically found was that the vast majority over 99%, like 99.9%, right? Passed through undeflected. So we're basically saying, okay, 99% of the time, they just went bang, straight through. Now, some of the time, there was deflection. So some of the time, there was this, or something like that, right? But what really shocked them was that rarely, but definitely this does happen, it would sort of be deflected backwards or at large angles. Okay. And so this third one was really the thing that really, really shocked them. Okay. And the reason why that really shocks them is because helium is quite dense. Like a helium nucleus is quite dense. So as far as the scientists in their own words back then, they were basically saying, you know, it was as shocking as if, you know, you fired a cannon shell at a piece of tissue paper. So this is your tissue paper, this is your cannon shell, you fired it, and it didn't go through, but it came back and hit you. Right? So that's how shocking it was for them, because as far as they were concerned, this is like a cannonball, and this is like a tissue paper. So going through, yeah, not that surprising. I mean, it was more, you know, a few other things, but this particular fact that it could ever come back was really, really concerning for them as far as the theory goes. And this alpha particle is, you know, a helium nucleus, and it's got a 2+ charge, and, you know, it's got, you know, 2 protons and 2 neutrons. So it's pretty heavy and pretty dense. And so they're basically expecting it to kind of just go through. So if anything can kind of hit it back, what that really means is there must be something in here good enough to have the capability to knock back a helium sort of nucleus. So it's a bit like, you know, if you have like a tank, right? And you're just driving through, you expect the tank to just go, drive through. But if you send tanks and most of them get through, but some of them get like thrown back, you kind of sort of must have Superman in there or something, right? There must be a person who, you know, when you go in, the tank gets thrown back out. Not very often, but someone like that must exist in there. So as far as the atom goes, then what we're saying is the conclusion is there must be, has to be, a high concentration of mass and charge in the atom. And that gives rise to what you've already studied as your nucleus. This is where it starts. So there's no way that Thomson's plum pudding model would be able to explain the sort of backward, because Thomson's plum pudding model is sort of violated in many ways because, you know, well, one, you know, it shouldn't just go through without anything if most of it's taken up. And secondly, you know, it's certainly, you know, it's not strong enough to push back. So this is where you now have Rutherford's model. And this is getting closer to what you've learnt, but it's lacking a few details. So Rutherford's model is basically, okay, fine. To be able to have a concentrated amount of mass and charge in one spot, you know, that's got to be your nucleus. So this is your high concentration of mass and charge. And because it's highly concentrated, it must be very small. And just to be clear, when we say small, I mean, you know, you guys are probably in rooms that are what? 5 meters big, let's say, 10 meters big. Well, let's say it's a slightly smaller, you know, if it was a slightly smaller room, like 3 meters, then if your room was the atom, if your room was the nucleus, then you'd basically need the atom to go all the way to Canberra, right? If your room is like, 5 meters, then the atom needs to go to Coffs Harbour. So basically, think all of New South Wales. And if your room is 10 meters, then the atom needs to go to Melbourne. So it gives you an idea of what we mean by the nucleus is small. But we're not saying it's small because, an atom is also small. We're saying it's small relative to the atom. And Rutherford didn't pay too much attention to the electrons. He just said, well, because he didn't know too much about them, but he just went, okay, well, electrons go around the outside. So his model is basically, a nucleus where the protons and neutrons are. And this is small. It's in the center. And then you've got, electrons sort of orbiting the nucleus. Now, this is better than the original model because it does help address these issues. Because now, how does it address that? Well, because how does this addresses the experiment results? Well, because we're saying that nucleus is really small. This is not to scale, right? If it was to scale, you can't see the nucleus. But because the nucleus is so small, then basically we're saying the atom is, 99.99% empty space. Which means most of the time, I'm just going to go, whee, and pass through. Like you're not hitting anything, right? Because it's, think about, oh, well, if someone decides to just randomly point on the map, will they likely pick your room out of anywhere in New South Wales? I mean, they could, but it's much more likely they're going to pick somewhere, if it's just purely random, it's much more likely they're going to pick somewhere that's very, very far away from where you are, right? Certainly not far, not close enough for you to say, okay, you got my room. So that's most of the time. Now, every now and then you might get closer, and so you might get something like, okay, I'm getting a bit close, and so I sort of deflect like that, because, this is positive, right? So it's a repulsion. But very rarely, but possibly, you kind of get very close to the nucleus, and so it is stronger than the helium particle, and it knocks you back. And it also, explains the ability to deflect backwards. However, Rutherford's model does have some problems, which they already knew at the time, but obviously, they didn't know how to fix them yet. And it was already better than before, so they kind of went with it. But the problems include, under classical theory, so sort of think Maxwell, classical theory says that if you've got a charge that is accelerating, then it will get a change in an electric field, which will generate a change in a magnetic field, and repeat, which means that there will be an electromagnetic wave emitted. So that means as this goes around, the electron, as it goes around a circle, will emit electromagnetic waves. So basically, electron in circle means it will emit electromagnetic waves, which means it will lose energy. And therefore, that means if you think of this like a sort of, what we covered in space, if it loses energy, it will spiral in. And it can't stay in orbit then, if that's the case. Well, So that means we're saying that all atoms aren't stable then, which we know is nonsense. But I guess that's the best Rutherford could do at that point in time with his model, with the limited information he had. So that's one big problem, right? We don't know how the electrons sort of behave. And we most certainly know that although we say they're kind of on the outside and they're going around, we know that can't actually be right because, well, if it was, something is either wrong with the model or something is wrong with classical theory, or both, as it turns out to be the case. But, your classical theory would say that this can't happen. It cannot be stable that way. Okay? So, therefore, what we end up happening is that we would then need to update this as well. So the next part is we're going to talk about how this was improved by Bohr. So Bohr's model of the atom is getting more close, again, to what you guys understand, and it's probably what you guys more or less think of when you do it. You probably don't use the Schrödinger model too much, although that's probably the real sort of more advanced one. You might use it in words, but you haven't really done calculations with them. So Bohr's model is very similar to Rutherford's. So you still have your nucleus in the middle. You still have electrons going around. But Bohr now basically adds rules about how they go around. And so essentially Bohr starts off the idea kind of your electron shells. So Bohr's model of the atom is kind of like Rutherford's, but he added 3 postulates. He kind of tried to fix Rutherford's issue. So number 1, he just goes, electrons can basically orbit around the nucleus at certain stationary states. So electrons can only orbit the nucleus at certain sort of stationary states. So instead of allowing you to have any radius you want, so you can't just go closer or further out anywhere you want. You're either here or here or here, right? So there are only certain points where you can be. You can't be in between, not in between. So basically, he's now basically made energy levels of electrons discrete. All right. And again, this is after Planck. So this is basically starting to use Planck's idea, which of course no one was happy with, but, ends up being convenient every now and then when you want to explain something that they can't explain. So firstly, the idea is, well, electrons can no longer just orbit anywhere they like. They have to be at certain sort of what he called stationary state positions. And electrons are allowed to move between states. But these stationary states, of course, well, I mean, kind of like think of what we said for space, which would basically apply for this model, but not for the Schrödinger one. So, you've got an electron going here. And so as you go out, you're going to gain energy. Because, this time you're gaining electric potential, right? Whereas in our sort of space, you're gaining gravitational potential, but you're gaining potential energy. Whereas if you kind of go this way, you're losing energy. So electrons can move between stationary states, but, well, obviously each stationary state has different amounts of energy levels. So electrons can, move between stationary states, but since the energy levels are different, they will, either by, absorbing or emitting electromagnetic waves. I probably should have added another sentence here. So we said that electrons can only orbit the nucleus at certain stationary states, not in between. And importantly, to deal with sort of Rutherford's issue, is that, and they do not emit electromagnetic waves in these states. Right? So Bohr just basically goes, well, one of the problems is that they emit electromagnetic waves. I'm just going to say they don't. Okay? At certain points, they just don't, is his solution. There's not really an explanation, but again, they had limited information and they do their best with what they can. And so kind of like Planck, he can work something out, doesn't mean he's got a real good explanation for it. Bohr is in the same similar situation. He was trying to work out certain things about the hydrogen spectrum, which he was able to do, and that's, but that doesn't mean this is a good explanation, because it's not really an explanation. He's just saying, well, don't ask me why it doesn't emit electromagnetic waves, because our theory says it should. I'm just going to assume it doesn't. Okay. So electrons, when they're going around in a stationary state, do not emit electromagnetic waves. But if they want to go to another one, they can. But to do so, they need to change the energy level, which means you either need to, well, go up in energy level by absorbing electromagnetic wave. So this is, absorb. Absorb the electromagnetic wave. Or in this case, emit the electromagnetic wave to lose the energy. All right. And of course, the electromagnetic wave's energy must equal the change in the energy level between the shells. And this, of course, has a whole lot to do with your, AAS and all your spectroscopy, right? It is basically the fundamental reason behind it, and all your line spectrum and all that. Now, the last thing Bohr basically said is basically, he says, stationary states occur when NVR equals NH over 2 pi. So that's basically Bohr's model. So Bohr's model basically takes Rutherford's model and just adds some conditions onto it. So he basically starts the idea of these electron shells. You've got these stationary states where they don't lose electromagnetic waves. And, well, he doesn't have any explanation for why, but he can say, well, you can move between them by absorbing or emitting electromagnetic waves. And, he gives you a mathematical condition for that. Okay. Now, Bohr's model is an improvement on Rutherford's because, well, it helps sort of explain hydrogen spectra. So it helps explain why you can have spectral lines, right? Why elements have spectrum lines. It also sort of starts to, introduce the concept of electron shells, which sort of helps understand the idea as well about sort of the reactivity and all that kind of thing. But it actually has quite a lot of weaknesses as well. The key one, of course, is that it is a mixed, well, like I suppose the key one is that it's not an explanation. He can't explain his postulate. He just said so. He can't say why stationary states exist. All right. Another thing about his, postulates is that, well, it is a mixture of classical and quantum physics. So, he's used Planck's constant, nh over 2 pi, but he's also using classical physics to kind of, you know, talk about how to sort of calculate the energy levels and all that kind of thing. And so it's really a mixture. And fundamentally, classical physics and quantum physics have different assumptions. So you really didn't have, you know, like, you know, you really should be clear about what you're assuming and not just go, well, I put these things together and I can get the answer, right? But get the answer for, you know, Balmer's equations he did, he can sort of explain and predict, you know, Balmer's equation. So the hydrogen spectrum, as we mentioned earlier, you know, as, you know, empirically determined and, you know, and basically conforms with Balmer's equation, which is the question that uses, you know, which nowadays for you guys, you'll basically be using sort of this formula. And basically we can calculate the wavelength of the electromagnetic wave emitted based on which cell they jump from and which cell they jump to. And, you know, a bit of common sense hopefully would be able to see that the further out you are and the higher the energy level and the further in you jump, the bigger the energy difference. And so, you know, because E equals HF, the bigger the energy difference, the higher the frequency, which means the shorter the wavelength, right? Okay. Other, you know, other weaknesses which you'd really only start writing if you're talking about sort of extended response questions is, well, the fact that it cannot explain hyperfine lines, Zeeman effect, which, you know, you don't know exactly what these are, but basically Zeeman effect is how, you know, how the spectral lines behave a bit differently under the magnetic field. If you know, apply a strong magnetic field, you'll see sort of the fact that it'll split. Okay, and it cannot explain, you know, spectrum of more complicated atoms. You can do it for hydrogen, but not for more complicated atoms. And it cannot also explain the difference in intensities between the spectral lines. So it can tell you if the line will exist or not, but what it can't tell you is if that line will be bright or not, and why. Okay. So as a result of that, next thing we're going to go and do is we're basically going to get Bohr's model to be upgraded by de Broglie. But see, de Broglie didn't really set out to improve Bohr's model, although he ended up being able to do so. De Broglie was actually looking at something else. And basically, he was looking at matter waves. And you've got Einstein's E equals mc squared, and you've got Planck's E equals hf. And you don't remember that, you know, if this is for electromagnetic waves, then this is hc over lambda. And so if you equate the two, you'll get mc squared equals hc over lambda. So lambda must equal hc over mc squared, which means h over mc, which we can rewrite as h over mv for, you know, things that aren't the speed of light. And therefore, we basically say that de Broglie is saying that all matter has a wave property. So that's the sort of formula behind de Broglie. But let's probably talk more about the implications. You need to understand that, for example, let's take a look at something like light. Right? And we went, okay, Some people said wave, yes, yes, yes. Some people said particle, yes, yes, yes. And they thought about it. And, you know, until they went, okay, it can be polarized. Okay, it undergoes interference. Okay, it's a wave. And finally, that question was settled, right? Until, of course, you go to a photoelectric effect. And then people fight over it again and go, well, we know light is a wave, but, you know, if we think of it as a particle, we can explain the photoelectric effect. And so people go, well, okay, fine. I mean, we've said for quite some time now that light is a wave. And, you know, clearly it does things that only waves can do. No doubt about that. A particle is not going to diffract. A particle, you know, from our understanding of what a particle is, it's not going to diffract. It's not going to superimpose. Can't have a particle being more than one place at the same time. So it's okay, it's definitely a wave. But if you think of it as a wave, using our wave theory, then you can't explain the photoelectric effect. And so people go, okay, well, fine, let's just fudge it. Let's kind of, you know, imagine that it is a particle for photoelectric effect. And so, okay, fine, 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 right? That's the idea. But what that basically ends up meaning is, at the end of the day, with this photoelectric effect, you're saying that light can be a wave, and you can say it's a particle. And so light has both wave and particle properties. It's able to exhibit wave properties as well as particle properties. Now with de Broglie, he's saying that matter, such as, you know, matter, so things that are clearly particles, he's saying matter can be waves too. Okay. So this basically leads into the idea that we've got light being an example of waves that can act as particles. But because of de Broglie is saying matter, and clearly that's particles as far as we understand it, can act as waves. So for that reason then, we're saying that, well, we've got this idea of wave-particle duality, in which anything, whether we call it a wave or whether we call it a particle, but basically everything has a wave nature and a particle nature. Because see, you need to understand that waves and particles are that things we made up. They're things we decided, and we made up rules about how waves behave and how particles behave. But that doesn't mean that that's how nature works necessarily. So, you know, if you make up black and you make up white, maybe there's no black and white in the world, and there's only gray. Now, some things that look very, very black, so we just call them black, and some things look very, very white, so we just call them white. But some things are right in the middle, right? So some things like light, you know, you might focus on the darker parts in certain ideas, and you might focus on the lighter parts in other points. So wave-particle duality is the fact we're saying that anything can now act both as a wave and as a particle. And this was actually, you know, you can refer to the Davison-Germer experiment. But this is an experiment involving electrons, which at this point in time we clearly know are particles. But what we did was we found that these electrons were discovered to exhibit diffraction, which is clearly a wave property. And this was discovered after the Broglie's theory was published. So this is basically experimental evidence for de Broglie's theory. And so de Broglie, which says, okay, your electrons can act, or all matter, such as electrons, all have a wave property. And that's basically the gist behind de Broglie's idea. And the thing with that is you can use that to explain Bohr's model. Because Bohr, remember, had a postulate which said NVR equals NH over 2 pi. Now, de Broglie said that your lambda must equal H over mv. So if we do a little bit of rearranging over here, we can get 2 pi r equals n times H over mv. And if we just replace that, we're saying equals n lambda. So another way to think about, Bohr's postulate is that you've got 2 pi r equals n lambda. And how does that work? Well, imagine this is your stationary state. Then 2 pi r will just be the circumference of the circle. Now, n, remember, is an integer. And lambda here is the wavelength of the electron. So another way to explain this is simply that the stationary states are when the circumference of the circle, or if you like, the length of the orbit, is a whole number multiple of the wavelength of the electron. And that might look something like this. So this is the opposite. So that just to be the opposite. So note that this is not 1. So this will not work. And the reason for that is you can probably see the electron wave will interfere with itself. So it's not stable. On the other hand, if we had something like this, then this will just repeat, right? So basically, we can think of it as, this is okay. Basically, we're saying that it's a standing wave pattern by the electron. And that is basically de Broglie's picture. Now, this atomic model is then further enhanced by Schrödinger. So Schrödinger basically, along with Heisenberg and Pauli, this is getting into the early 20th century, like around 1920s to 1930s. they basically then moved from quantum physics to what's called quantum mechanics. So people, I guess, often hear of the word quantum and think of it as the same thing. No, they're different. So you've got classical physics, you've got sort of quantum physics, which is like sort of the start, and you've got quantum mechanics. So it's a bit like, what's the difference? It's a bit like, okay, so you used to have cars, right? But cars can't really fly, but we want to fly. So how about we just add some wings onto a car? If you add some wings onto a car, yeah, maybe you could get it to fly, but it's not going to fly very well, right? So as a result of that, what you end up doing then is you would actually want to make a plane, right? You want to make it a plane from the start. And that's what quantum mechanics is. You're kind of getting rid of all the classical physics, all right? You're not making any assumptions of classical physics. You're not trying to work within the framework of the old system. You're making an entire new system. Whereas quantum physics kind of was before they did that, and it was still kind of sort of still, well, it mostly works. So how about we just, the only final thing we need to do is just add a wing, right? So no, quantum mechanics is sort of building everything from the ground up. And basically, Schrödinger has then essentially made it so that he's got this sort of wave function, which then interprets everything in terms of probability. So when you talk about chemistry, when you talk about your electron cloud, that's really talking about your Schrödinger. So your electrons don't really orbit in a particular radius or anything like that. They've got this entire probability distribution associated with it. Heisenberg has what is called his uncertainty principle, which states that whenever you measure anything and you've got a pair of variables, one of them, there is a sort of fundamentally at the sort of physical level, there is an uncertainty. No matter how well and how good you make your instrument, as far as physics is concerned, fundamentally, the thing you're measuring itself is uncertain. Okay. If you're trying to make something more accurate, you might be able to achieve that, but it will be at the expense of inaccuracy in something else. And so there's more than one example of that, but your typical pair is between your location and your momentum. And we're saying that the product of that must be greater than or equal to h over 4 pi. So if you're trying to make the error in your displacement, if you want to know exactly where a particle is, what you won't be able to know very well is its momentum. If you want to measure its momentum very well, you might be able to do that, but you won't know where it is then. Okay. Now, we also mentioned Pauli. So Pauli had what is called his exclusion principle. And basically, the exclusion principle says that no particle can have the same quantum state. And the quantum state, basically, think of it as a bunch of numbers. And so the bunch of numbers can explain the quantum state. But this basically explains your chemistry, electron shells. Why does the first shell have one subshell? Why does it hold 2 electrons? Why does the second shell have an S and a P and hold a total of 8 electrons? Why does it, your third shell have an S, P, and D, and why does that hold 2, 6, and 10 electrons, and so on? That basically comes from Pauli's exclusion principle. So we'll need to then go through how the radioactive decay of nuclei. So I've mentioned this a bit before. Radioactive decay is basically a result of nuclei that wishes to become more stable. And it does that by, I guess, increasing the binding energy per nucleon. All right. Now, your decay, you'll need to know the different types of decay. So you know that there's sort of alpha, beta, and gamma decay. You need to know their properties. So you need to know what they are. Helium nucleus, this is generally an electron or a positron. Okay, and this is an electromagnetic wave. And based on what they are, then you should be able to determine their sort of mass. So this is about, relatively speaking, this is about 1, this is 0, this is roughly 4,000. You need to know their charge. This is positive 2, this is minus 1 or plus 1, depending on if you're talking beta positive or beta negative. This is 0. You therefore need to also be able to work out their, deflection by electric fields, and that's going to be quite clear, towards the negative. This is going to be towards the positive, this is towards the negative. This is no deflection because it's not charged. Deflection by magnetic fields, well, basically as a positive charge would deflect, as a negative charge would deflect, as a positive charge would deflect, and no deflection. What you would need to pay special attention to is its ionizing power and its penetration power. So the ionizing power is high, medium, low. The penetration power is the opposite to that. So it's going to be low, medium, high. Okay. To be clear, when I say low penetration power for alpha, it's sort of saying, paper can probably stop it. If we say moderate for beta, then we're basically saying, okay, the aluminum foil, thin aluminum foil should be fine. If we're talking about a, penetration of being high for gamma, then you're basically going to need, you're going to need lots of concrete and lead. Now, as for why the mass of this is 4,000, well, because it's a helium nucleus. So helium nucleus is made up of 2 protons and 2 neutrons. And yes, I should probably say that's closer to 8,000 also. Okay. Because a proton and a neutron is roughly, 2,000, very roughly, and you've got 4 of them, so it's closer to 8,000. 7,000 something, but it's just there to give you a rough idea. And so basically the point is that an alpha particle is much, much, much heavier compared to a beta particle. All right. So alpha is going to emit a helium nucleus. Beta will either emit an electron plus an antineutrino, or beta positive will emit a positron plus a neutrino. And gamma simply emits gamma. The mass is relative mass. So if we let electron be 1, we're just talking roughly. Okay. You can convert them into kilograms if you want, but it was more an idea of, to give you an idea of, how many electrons there are, if you like. Okay. So you understand that radioactivity, the rate of decay is proportional to the amount remaining. And so you guys are probably comfortable with this from your rates of decay in 2-unit maths. So I won't go through it too much, but basically you've got these sort of formulas. And you've got your lambda equals log 2 over t, which you can probably derive from maths. But those are the formulas you may need to know when you're calculating with regards to half-life. Now, that's radioactive decay. Now, you also need to understand basically nuclear fission. Now, I've mentioned this before. Nuclear fission is basically the act of a large nucleus splitting up into smaller daughter nuclei. They're called, daughter nuclei just because, well, they're smaller. And again, as usual, it does that to become more stable. And it does that because of the fact that it will increase its binding energy per nucleon. Now, to make the large nucleus, split up, we often need to destabilize the nucleus. I mean, it's not very stable already, but it kind of would help if you made it more unstable. It's a bit like if something's about to fall over and you want it to fall over, then it would help if you push it over, right? I mean, it's not, he might, if someone's about to fall over by themselves, they might, but they're kind of almost falling over. And if you push them over, well, they're definitely falling over. And that's what we're kind of doing, right? The nucleus itself is already unstable and we're giving it an extra push, all right? So in nuclear fission, you're basically trying to find you're writing the equations here. And basically just make sure when you write your equations that for nuclear fission, you typically start with a large nucleus. You add neutrons to destabilize. And you end up with your daughter nuclei. But if you want a sustained reaction, so you want this reaction to go on by itself, what you also need is neutrons to be emitted. Okay. Because the point of it, of course, is, if you need a neutron to start this reaction, you need another neutron to do the next one. And so you basically just keep getting the neutrons to, keep making it happen, all right? Now, when you do your reactions, because you may very well be asked to write your reactions, just make sure that your atomic numbers balance. So basically all of, the sum on the left equals the sum on the right. And make sure your mass number balance. And again, your sum on the left must equal the sum on the right. Okay. So, that applies for all your nuclear chemical equations, including the decay ones. So the decay ones, because if you're having a helium nucleus or otherwise, then that makes it sort of easy. Now, as far as your, nuclear fission goes, what you'll end up having is let's say you start with the uranium-235. Now you can look up the atomic number, which is 92. Okay. And what we'll basically do is we'll make it split. So we'll add like a neutron. Now, once we add a neutron to this will become more unstable. So, we normally won't write this out, but, it will have this for a little while, right? For a very, very, very small amount of time. Now, that is going to be problematic because uranium-236 is not very stable. So it can then decay into smaller parts. And you don't really know for sure what it's going to decay into. I mean, it could decay into, it's based on probability. So it could decay into, for example, krypton, or, bromine. So for example, you might have various situations. it could go into, you know, that's one example. So notice that 148 plus 85 plus 3 is 236. And notice 57 plus 35 plus 0 is 92. That's really what we're looking at here. But that's certainly not, you might go, well, how do I know it's 148 and 85? And the answer is you don't. I mean, not unless you're told, because just as easily, well, maybe not just as easily, but, you know, it's very also possible for this to happen. And those aren't the only, you know, reactions either. I mean, you could, you know, have this happening. I mean, in reality, they all happen, I suppose. It's just how much each happens. So I guess, you know, it's random, right? There's a probability involved. So when you're asking, how do I know which happens? Well, the short answer is you don't. It's a bit like saying, well, if I toss a coin, how do I know if it's heads or tails? Well, until it happens, you don't. Now, sometimes you'll get heads. Sometimes you'll get tails. You do it enough times, maybe you'll even get it to land on its side. Not very often, but it will, but it can happen. And so same thing with fission, right? There are probabilities involved. And as far as you're, you know, as far as you're concerned, you know, you'd have to be given information for them to know what you want, they want you to write. But you are definitely expected to be able to fill in the blanks based on the fact that the sum of the atomic numbers are the same and the sum of the mass numbers are the same, right? Now, this is, you know, other examples of nuclear fission with regards to radioactive decay, just in case, you know, there was any sort of problem. So we've kind of done, you know, fusion yesterday, so I won't do fusion, but radioactive decay, if you're having trouble with that, you know, we could do examples. So for example, thorium 234, 90. This is one, I mean, that could undergo multiple decay, but let's say it undergoes beta decay. So we tell you it undergoes beta negative decay. If it undergoes beta negative decay, we know it emits an electron, which means that it will emit an electron and an anti-neutrino, based on what we said earlier. But what we do know is we've got something here, and 0 plus something is 234. So this is 234. -1 plus something is 90. So this is 91. You can then look up what 91 is in the periodic table, and you'll find that's palladium. You know, you can do something similar. So on the other hand, if I tell you that I've got alpha decay, and I've got uranium, let's say 238, and I'm telling you it undergoes alpha, then you know, based on what I said earlier, that you're going to get a 4He2. And 2 plus something is 92. So, well, that's got to be 90. 4 plus something is 238. So that's 234. Then you look up what 90 is, and that will be thorium. So those are basically how you would sort of write your reactions like that. Okay. Gamma is a bit less interesting, and you probably won't be tested on gamma because gamma, there's no change in, you know, it's just gamma. If it was pure gamma, so you're just going to have something from what's called a metastable state, so semi-stable to a more stable state. But you won't really get any change in the sort of atom. You just get an asterisk to no asterisk. Okay. Now, all of this sort of radioactive, you know, transmutation and all of these things, whether it's nuclear fusion or fission, all relate to the stability of the nucleus. And the stability of the nucleus is measured in, you know, binding energy. So basically, binding energy basically refers to the energy that would need to be supplied to, you know, break apart the nucleus. So therefore, basically, because binding energy is the energy that needs to be supplied to break apart the nucleus, then basically the higher the binding energy, that means the more energy is required. So that means the harder it is to break the nucleus apart. So the more stable the nucleus. You may be asked to calculate binding energy. And binding energy is equal to E equals mc squared, where E is binding energy, but the m is the mass loss when the nucleus is formed. So basically, you take the mass of everything, and you'll need to be given the masses, all right? Because, you know, the mass loss is quite small, okay? So you'll need to be given things to like quite a few decimal places. So it's the mass of everything. So, you know, each proton, neutron, electron, etc. So you add everything up minus the mass of the molecule, of the atom or the nucleus, right? And there will be a difference. Now that difference might not be large, but there will be a difference. And basically we're saying that when the atom was formed, some mass was lost and became energy. And that energy exists in the form of binding energy. And that binding energy is what holds the nucleus together. In fact, when we're doing nuclear power, nuclear fission, nuclear bombs, that energy that is released is releasing that binding energy. Okay, that's what we're doing. Well, more accurately, we're letting their binding energy increase so that we can take out. So the nucleus loses energy to increase the amount of energy to supply that would need to break it apart. And so we extract that energy as nuclear power. Now, a question was asked about a neutrino. And so it's very clear that we've sort of explained it. It's very clear cut. If you undergo beta, then you'll get an anti-neutrino. If you've got beta positive, then you get a neutrino along with the positron. End of story. That's, you know, all you need to know, basically. Okay. Now, in terms of the, I mean, there's a bit of a sort of explanation, I suppose, and a bit of questions on binding energy. So I'll leave you guys to read more on the standard model because that really is just content. And I'll rather instead perhaps spend more time on explaining the binding energy since there's lots of questions about that. So short version is consider your nucleus. So your nucleus, right? It's made up of protons. And let's just think of two protons. Now, protons are positive. And if two protons are positive, and remember the nucleus is very small, that means they're very close together. Now, you may or may not remember the formula from year 11, but there's this formula called Coulomb's law, which calculates the force between two charged particles. And, you know, if they're both positive, then they're going to repel each other. K is quite large. It's 9 times 10 to the power of 9. And distance is small. But the point of the matter is the closer they get, the bigger the force. And this force is pretty big. So theoretically, you'd expect that these protons can't get together because there'd be a force of repulsion. All right. So in a way, it doesn't make sense that your protons are close together, because the protons would really repel each other very strongly, in fact, given the fact that they're so close, and electrostatic force is, well, not exactly negligible. It's pretty strong. Gravitational force is negligible in this context because, the masses are so small, but the electrostatic force is actually quite strong. And you can calculate it, and it's pretty strong. So how do we explain the fact that they stay together? Well, there's got to be some other force. And that would be your strong nuclear force. So we're basically saying that in addition, so it's not that they don't repel, they do, to the force of repulsion, which is electrostatic. There is also the force of attraction from your strong nuclear force. And because the strong nuclear force exceeds the electrostatic force of repulsion, well, you would hope so anyway, but when it does, then sort of your atom remains stable. Now, the thing is, the general rules of atom stability are very, kind of simple, all right? The atom can't be too big. Or more specifically, the nucleus can't be too big, right? The nucleus can't be too big. And basically, atomic number, greater than 82 means it's unstable and it will, decay. And this one is this relates to your strong nuclear force. And we'll explain that a bit. The second rule, which we won't really explain, we'll just tell you what the rules are, is basically you need a neutron to proton ratio, around 1. Although, the required ratio increases as P increases. So those are your probably two main rules. And this one relates to what's called the weak force, which we won't really get into details because it's a bit hard. But basically this one relates to, the electroweak force relates to beta decay. This one relates to alpha decay. So it can hopefully explain alpha decay a bit more, but beta decay, you'll just basically memorize it, okay? And that's beta decay, think of it kind of, it's not right, but kind of think of it like, see, in this case, the mass number didn't change, but you got an extra proton. So kind of think of it like a neutron became a proton. Now, I stress that this is not really accurate. Like it's not, I'm missing out details, but you can, to help you think about it, not that this is actually accurate in terms of the actual sort of what's happening, but you can think of it like the neutron is a proton plus an electron. Not really, but kind of. And so what has happened is the neutron has split into a proton and an electron, and it's given off the electron because it didn't want it, and it kind of became a proton, and that's your beta minus decay. And perhaps I'll add a column to one of my earlier columns here. All right. When do these decays occur? Alpha basically occurs when the nucleus is too big. So think greater than 82 for your atomic number. Beta basically occurs when your neutron to proton ratio is either too high or too low. And gamma basically occurs when your nucleus, you know, is not at ground state. So gamma basically occurs when your nucleus, just think of it like, okay, you've got something that needs to sort of, you know, cool down a little. So your the nucleus's version of cooling down is emitting gamma radiation, all right? It's got some excess energy it needs to get rid of. It releases gamma radiation. Now, beta is to adjust, it's all to do with the electroweak force, and it's basically, you know, going to result in adjusting the sort of neutron to proton ratio, either up or down, right? If it's, you know, if it's a beta negative, like here, then what's happened is you made the proton numbers go up. So that means in this case, the neutron to proton ratio is too high. You've got too many neutrons. So we're getting rid of a neutron to, you know, get a proton basically. On the other hand, you know, we could have a beta positive. We can have a beta positive one. That's possible as well. So just, you know, write an example for that in case there's any confusion. Should be enough space. So your beta positive might be something like, you know, okay, let's say I have carbon 14. It will emit a beta positive, all right? Because it's emitting beta positive, you'll emit a neutrino as well. So there's no bar on top of it because this is the neutrino, this is the antineutrino. So you can put a bar on this one if you like. Technically, you probably should, but many people leave it off because this is the antiparticle. And again, you know, numbers matter. So that's got to be 14. And this was too many neutrons. Oh, I did it the wrong way. So if it's beta positive, I should really have something that's got too many protons. All right. So if I did this, just so you know, if I finish this off, this would not undergo that. This would be, you know, because it's going the wrong way, it would be, you know, you would need to bring that number up. So this would be a -1, E, you know, 0 plus antineutrino, and you get nitrogen 7. All right. So that's not what would happen. I'm not going to get beta positive. Let's see if I can think of an example for beta positive. So beta positive, I need too many protons. Now, if I have too many protons, what would have too many protons? That would be a good example. So let's say I did carbon 11, for example, all right? So we know carbon generally is 12. So 11 has too many protons compared to neutrons then. So this is unstable. So it will do that. You know, in physics, to be honest, most of the time, most people leave off for the positron anyway, most people leave off the bar. So we'll just leave it off, all right? And again, you'll need to make the numbers match. So 1 plus something must equal 6. So this must be a 5. And 11 must equal something plus 0. So that's an 11. And so look that up. And 5 is boron. And that's it. So that's your beta positive. Hopefully all fairly straightforward. Okay. So back to the sort of strong nuclear force then. The reason alpha particle decay occurs, as we said, is because of the strong nuclear force. And basically the strong nuclear force is very strong, but it has a limited range. So basically, you know, as your nucleus gets quite big, all right? So, you know, imagine you've got your protons. So protons are, you know, red. So as your nucleus gets bigger and bigger and bigger, you're going to have more protons in there. And remember, protons do repel each other. It's not that they don't. They just, you know, they just have strong nuclear force between them. But the problem is that because they all repel each other, then if you're this, you know, proton over here, the more protons there are, the more you're being pushed out, right? This in terms of, you know, electrostatic force. Now, we did say that there's a strong nuclear force, but your strong nuclear force has a limited range. So once your nucleus starts getting bigger, you might only get the strong nuclear force from these ones, right? You might get attraction from these ones. But that means everyone else here only repels. This, you know, we're focusing on this particular sort of, we're focusing on this proton. So, I mean, from this point of view of this proton, as you add more and more protons, well, it's just getting kicked out more and more, because at some point it's going to reach the you know, the limit of how many sort of ones are near it as far as the, you know, strong nuclear force can go. And so the strong nuclear force can't grow anymore, right? But the force of repulsion will grow. And so as you get bigger, the repulsion will start getting, you know, more equal to the nuclear force, and you're going to start breaking the nucleus apart. And that's when you know, shoot out your helium nucleus. And why is it a helium nucleus as opposed to a proton? Well, again, that comes down to your binding energy. And basically, I mean, I've drawn this before, but you might want to refer to your textbook for a bit more detail. But basically, and you know, you don't need to know these details, but basically, the helium nucleus, you know, is like it's the most binding energy per value. Like, it gives you the most value. It's like when you go to a shop, you know, you could buy milk, like, I don't know, you can buy milk or things for like different packet sizes, right? And helium is the cheapest packet size, basically. All right. It's the cheapest per, you know, if you want to buy a few things, you want to buy as many as you can get, this is the cheapest one per unit, right? So it provides the highest, you know, gain of binding energy per nucleon around this level anyway. And the reason why adding more and more neutrons, you know, increases stability is because neutrons do not repel protons. I mean, they don't have charge, so don't repel. But what neutrons can and do is they do attract, because a strong nuclear force has limited range, but it is an attractive force between nucleons, which means between, you know, protons and neutrons, and between neutrons and, well, yeah. As far as you're concerned, what's important here is between protons and neutrons, as well as, you know, protons and protons, I guess. But, you know, that's why as you get more and more bigger, and as this molecule gets sort of more and more unstable, you actually need to add more neutrons to try to keep it stable. All right. So hopefully that helps with that. Now, I'll just briefly go over the standard model, and that will kind of draw things to a close for the rest of the sort of course here. I think some of you are having difficulties with the nuclear sort of reactions. And look, it's very simple. It's just a chemical reaction. It's just balance the mass numbers, balance the, you know, atomic numbers. It's basically it, all right? Obviously, you need to know what a helium nucleus is, an alpha particle is, which is a helium nucleus. You need to know what beta positive and beta negative are. But really, that's all it is. You just balance out the mass numbers and atomic numbers. It's just that easy, all right? So we'll need to basically briefly cover essentially what's called the standard model of matter. Now, this is something that you can probably look into your textbook, because it will all be there. But hopefully I can help you figure, you know, classify a little. And basically the standard model of matter is, you know, you want to classify particles, because we have a lot of different types of particles now. You know, we used to just go, okay, there's an atom. Then we went, okay, well, there's a proton, neutron, and an electron. And electrons go around, protons, neutrons kind of are in the middle. You know, we said that, right? Electrons go around, protons, neutrons in the middle. But, you know, in the 20th century, we found that, you know, these are not fundamental particles. So despite what Thomson did, over 100 years ago, despite what Millikan did and so forth, and where they thought these were fundamental particles, we've now found that basically protons are made up of smaller particles. We call these quarks. And similarly for neutrons, right? And you do need to know the composition for proton and neutron, so I'm going to write them out. So proton is driven by an up, up, down, and neutron is, by, up, down, down. So U refers to an up quark, D refers to a down quark. Now they all have a lot of sort of properties, but basically, just to convince you, an up is 2/3 of your proton's charge. A down is negative a third of your proton's charge. So if you have, 2 times 2/3 minus a third is +1, and 2 times negative a third plus 2/3 is 0. So that, you don't need to know the composition of every single sort of particle, but you do need to know the composition of protons and neutrons. You are expected to know those. And basically the point of the matter is, we've now found that protons and neutrons are no longer our fundamental particles. They're made up of things called quarks. And then we did more research and found a whole lot of other particles. And so we need some sort of way to sort of classify our particles, all right? And we also want a way to sort of, explain our forces as well. So your standard model basically is a way to classify all of these sort of particles. And we've got, many, many, many of these at this point. So you've got, I suppose, your matter particles. So generally, sometimes you'll see tables written a bit differently because there are few different ways you might classify these things. It's a bit like saying you've got a whole bunch of animals, right? And while there is some sort of general way to classify them, just like, you could classify them based on, okay, I will have, the sort of, mammals and reptiles, for example. But some people might classify them as, male and female, right? So, you could have, just because I've, done it a certain way, doesn't mean other books are necessarily wrong. It's just the classification is what it is. And there are some things where you could sort of classify at a later point in time. So if I did sort of mammals, and then I could go, there's a horse. Well, a horse can be considered a male or a female. And if it's a male one, it's a stallion kind of thing. So whereas someone else might go, well, it's male and it's a horse, right? So there are sort of things where the order could be changed. But in general, your particles, you can split into what are called matter particles, and you can split them into what are called, force-carrying particles. So these are what are called bosons, right? Now, within your matter-carrying particles, then you need to split them into what are called, leptons, and what are called, some people write it as quarks, but basically they're hadrons. So hadrons are basically made up of quarks. All right. Leptons aren't made up of quarks. They're made up, they're just, leptons. So something like an electron is a lepton. You'll notice I didn't give you a breakdown of a, electron. Now, hadrons are then split into what are called mesons and baryons. And basically, mesons are made up of 2 quarks. Baryons are made up of 3 quarks. Baryons are more stable than mesons because mesons only have 2. They're not very stable. So, for example, your proton and neutron would fit here. So clearly, your proton neutron would fit here, and multiple of baryons would make up your nucleus, which would make up an atom, and so on. Your lepton includes your electron, but there are actually 6 leptons plus their antiparticles, so quite a few there. And then you've got bosons as well, all right? So you can look up your 6 different leptons. And then you've got, each one will have an antiparticle. So you've got the electron, the muon, the tau. And then you've got the electron neutrino, mu neutrino, tau neutrino. So when we did earlier with the neutrino, that's also a lepton. And of course, there are the 6 anti-leptons. So everything has its anti. So there's an anti-neutron, there's an anti-proton, and so on. When we say it's made up of quarks, your quarks also are made up of 6 different types of quarks. So you can look them up. You've got your up, down, top, bottom, strange, charm. And you've got, each one will have its anti as well. So you've got your anti-up, anti-down, anti-top, anti-bottom, anti-strange, and anti-charm, right? And then you've got your force-carrying particles, and basically those are things that carry your particles, being your forces. So those are things like your Higgs boson, which has made quite a sort of fuss in the last 10 years or so, because it was experimentally proven, you know, in 2012, which I guess is a while ago now, but quite recent by, you know, in terms of history. So there's the Higgs boson, which was predicted in the 1970s, but recently discovered. You've also got, you know, your photon would count here, your sort of weakons would count here, and your gluons as well. And they kind of relate each to your force. So your photons, which is your electromagnetic force, your weakon is your weak force, your gluon is your strong force, okay? So there's quite a few details about the Standard Model, but what you know, that will all be in your book. I've given you a sort of very, very brief outline of the Standard Model, and you do need to know it because they can test you on it, but it is mostly a memorization exercise. So just understand that basically they're trying to classify a whole lot of particles based on their properties. And so the properties you might also see mentioned are based on whether it's based on the sort of weak force or the strong force. And if they, you know, if they're what's called a fermion or not, and whether they follow sort of exclusion principle. But those sort of details, you know, are details about the Standard Model. You are probably less likely to test about to that level of detail, but you do need to understand essentially what the Standard Model is and how it basically, you know, is for. As we mentioned, what it basically is classifying the models. You can look up the details in your book, which they should all be there, but hopefully what we've covered will give you a bit more of an idea so that when you go through it in your book, it makes a bit more sense. Okay, so hopefully you've all found the last few days helpful in terms of revising your course. So we've basically covered the majority of the theory, and we've tried to focus on things that you've all said you've had more difficulty with. So hopefully that's been helpful. Let me know, you know, how you found it. And if I don't see you before your exam in roughly a month's time, then, you know, study hard, best of luck. And yeah, make the most of your month, right? Good luck with your exam and see you all next time.